Hi, and welcome to a power tutorial over the fall semester review. Please have out your pink review sheet as well as a periodic table and a calculator. Okay, we're going to start by going over the very last page in your review sheet. If you have any questions, please feel free to ask me. Okay. So for the first part on the review sheet, and this is identical pretty much to what you're actually going to have on your final exam. The format will be just like this, but there will be different questions. So it's really important that you know this page. It's 20% of your final, so that's a big part. Okay, so isotopes. It says use the periodic table to fill in the missing information. So it's important to know an isotope is one type of this particular atom. Okay, there may be 3 isotopes for copper, but this is just one particular one. The top number here is actually something called the mass number. The bottom number is going to be the atomic number. So it's important that you know what you're actually looking at here. So the top number, go here, 65, and atomic number, 29. Okay, so this is a given from what information we're providing here. For this chart, it's really important to know ape man. And if you haven't heard ape man before, you should know it now. So what does ape mean? Ape means the atomic number is equal to the number of protons, which is also equal to the number of electrons. So just by having the atomic number, I have a lot of information here. I know the number of protons and I know the number of electrons. There's just one little piece that's missing now from our chart. Does everyone see that? Yeah? Okay. Then for neutrons. So how do you figure out neutrons? It's the mass minus the atomic number equals your number of neutrons. Okay, so if my mass number is 65 minus my atomic number of 29, and I actually gave y'all on my calculator, so hold on. I only had 32 next. Okay, so when we subtract, I believe you, but I'm going to do it anyways. 65 minus 29 gives me 36 neutrons. Any questions about how to fill in one of those isotope charts? Okay. Another important point to make here is mass number is different than what's on your periodic table. Your periodic table has average atomic mass, which is the average of all the different isotopes. Okay, and we'll work one of those problems later. Okay, so let's go ahead and move on to moles, which is everybody's favorite thing in chemistry. So for moles, it says convert the following by using dimensional analysis, show your work. Because we're grading these by hand, it's going to be really important you show your work. Okay, if you just have the correct answer, we're not going to give you that 1 point. We'll count it wrong. We have to see the work. So convert 1.23 moles of carbon dioxide to molecules. It's important that you know your conversion factor. So one conversion factor is 1 mole equals 6.02 times 10 to the 23rd molecules. So I'm going to use that conversion factor to start with moles and go to molecules. So I'm starting with my given, 12.3 moles. Okay, so knowing dimensional analysis and how it works, what needs to go on the bottom here? Any idea? Don't be afraid of me. You can answer questions. I can edit stuff out of this. Yeah. Okay, good. 1 mole is going to go on the bottom, and my 6.02 times 10 to the 23rd molecules is going to go on top. Okay, so the reason for that is we want moles to cancel. So these units are going to cancel, so I end up with molecules. And now I can just plug this thing into my calculator. So I'm going to plug it in, 12.3. And I'm going to multiply by 6.02 times 10 to the 23rd. And I get 7.406, actually 7.4046 times 10 to the 24th. How many sig figs should I round to? 3. Okay, so you want to round to the same number of sig figs as in your given. So since I have 3 sig figs here, I want 3 sig figs in my answer. So my final answer will be 7.40 times 10 to the 24th And what's my unit? Unit's going to be molecules. Okay, that's the only thing that hasn't canceled. So molecules is the unit. Questions about that one? That one's simple because it's a one-step dimensional analysis. And like I said, the ones on your test will be just like this, but it may be like 12.5 moles of, I don't know, boron trifluoride or something. I'll give you a different molecule and a different number, but it'll be the same process. Okay? Yes, ma'am. Okay, so the question was how to round this properly. You want to round to the number of significant figures in your given. So the given is the number you start with, 12.3, right? So that has 1, 2, 3 significant figures. So your answer needs to have 3 significant figures. So 1, 2, 3 significant figures. So the way that you round has actually nothing to do with decimal places here. If you're rounding and considering decimal places, you would have to either be adding or subtracting. Okay? And we can work one of those problems at the beginning of the packet in a little bit, so I can show you what that looks like. But whenever you're worrying or using dimensional analysis, you're always going to round to sig figs because you're multiplying. Okay? Any other questions before I go to the next one? No? All right. All right, so number 7. I'm starting with 144.1 grams of hydrochloric acid, and I'm converting to molecules. How many steps is this going to take me? 1 or 2? 2. How do you know? Exactly, because moles aren't involved, okay? So I'm going from grams to molecules, but I can't do that in one step. I'm going to go from grams to moles, and then moles to molecules. Okay, so it's going to take me 2 steps to do that. Here's step 1, and here's step 2, okay? So to go from grams to moles, I have to use the molar mass. So I get the molar mass from knowing what the compound is, hydrochloric acid, okay? So I'm going to go to my fancy periodic table. Hydrochloric acid is made up of 1 hydrogen and 1 chlorine. So I just add their masses together, 1.008 plus 35.453. So adding those together, and it depends who your teacher is, but I never round these. I have my kids do exact numbers. You may have a different teacher that has you round, but I typically don't have my students round. Okay, so what I got was a molar mass of 36.461. Okay, so all I've accomplished here is going from grams to moles. Well, I don't want to stop at moles. I want to continue and go all the way to molecules, right? So to do that, my 1 mole is going to go on the bottom, and my 6.02 times 10 to the 23rd molecules is going to go on top. And remember, with dimensional analysis, you are going to multiply everything across the top, then divide by what's on the bottom. And when you do that, we're going to get 2.379 times 10 to the 24th molecules. I always run out of space. Can somebody help me with the door, please? Any questions about number 7 and how that works? Yes? No? It's a 2-step. Okay. Okay, so number 8, convert 3.25 moles of helium gas to liters. Again, you're going to start with your given, which is moles, and I want to go to liters. So we know for every 1 mole, you have 22.4 liters. Multiply across the top, and you have your answer. It's that simple. And so the answer for this one is 72.8 liters. Okay, and do know we are going to provide those conversion factors for you. They don't have to be memorized. Is that what your question was going to be? Yeah. They don't have to be memorized. So all of these conversion factors, 1 mole equals 22.4 liters, or 1 mole equals 6.02 times 10 to the 23rd, blah, blah, blah. All of that will be given to you on your test. It does not have to be memorized. We do have to know how to use it. Okay? All right, are we good with moles? Any questions for me? No? Okay. All right, the next part says to calculate the percent composition of oxygen in lithium phosphate. So to get percent composition, what I need on top is the part. So what part am I emphasizing here? Oxygen. So I've got 4 oxygen, so I'm going to take the mass of oxygen and multiply it by 4. Hopefully by now you know oxygen is 15.999. If you don't have that memorized, you get a periodic table, so you're still good. And you get 63.996. Okay, grams. So that came from taking 4 times the mass of oxygen. On bottom, you want the mass of the whole thing, so the whole lithium phosphate. So you've got your 4 oxygens plus 1 phosphorus, and these I'm actually going to have to look up. So phosphorus is 30.974. Plus, it was 1 lithium or 3 lithiums? 3 lithiums, thank you. So 3 times lithium, which is 6.941. Okay, I get 115.793. Okay, times 100. So it's just a typical percentage. It's not really anything special to figure this out. It's the part, meaning the oxygen, divided by the whole amount, the whole lithium phosphate, times 100. Okay, and so when I put this in my calculator, 63.996 divided by times 100, I get 55.267589 blah, blah, blah percent. So again, you want to multiply. Usually on these, we'll tell you 2 decimal places or 1 decimal place. So 55.3% is the answer. Questions about how to do that? Yes. I got the 63.996 because it was asking me to calculate the percentage of oxygen. So do you see how there's 4 oxygens in the compound? So I took the mass of oxygen, which is 15.999. You just look that up on a periodic table. Oxygen's right here, times 4. That's how I got that number. Any other questions before we move on? Okay, so for number 10, we're actually going to use the answer to number 9. So determine the mass of oxygen in 225 grams of a sample of lithium phosphate. Okay, so this one is actually really easy, and I don't know why, but kids overthink it and they miss it. It's very highly missed, but it's very easy. Okay, so what I'm going to do is take the mass of my sample, 225 grams, times the percentage of oxygen, which I just figured out in the previous problem. Now, here's the deal. I can't just multiply it by 55.3. Okay, I'm going to get a bigger number. That doesn't make sense. You have to move the decimal twice. So you're actually multiplying by 0.553. Okay, so you're always going to move the decimal 2 times here when you do that, and you'll get your final answer. And your final answer for number 10 ends up being 124 grams. And again, you have calculators there if you want to verify that your answer is correct or the calculations that we're doing. Questions about 1 through 10? Are we okay? Yes? Okay. Y'all look so entertained and excited. Okay. Number 11 and 12 are electron configurations. Kids typically know this really, really well. So if you need me to explain something a little bit better, let me know. But I'm going to go through this fairly quickly. So here's a periodic table, right? By now, you should know this is S. This is the P block. What is this part called? D. And this part at the bottom is the F block, okay? Now, something simple to memorize that kids don't necessarily know, you have a hard time with your energy levels sometimes. So here's a way to remember your energy levels. S always starts with one S. P always starts with 2P. D starts with 3D, and F starts with 4F. So it's 1, 2, 3, and 4. So that there's no confusion on what energy level that particular block starts with. Does that make sense to you? Yes? Okay. So I always teach it that way. So when we are doing the electron configurations for something like sodium, we're going to start all the way at the top with something like hydrogen. You have a question? Yes. It does. Okay, so helium would actually be really nice over here, except for the fact that it acts like a noble gas. So that's why it's in that last column, but it is part of the S. Okay, so if we were just doing helium, it would be 1s2, and that would be it. Does that make sense? Okay. All right, good. So if I'm going all the way to sodium, like this one asks, it's going to be 1s2, going through hydrogen and helium, down to the next energy level, which is the second energy level, still in the S block, and I go through 2 atoms or 2 electrons, and I'm building on this cloud, right? So I'm going to go across to the other side. This is where I run into 2p. How many electrons are in that block? 6. Good. So my exponent is a 6. I'm going to go down to the next energy level, which is 3s. My exponent is just going to be a 1. Okay? And a way for you to check your work is to add your exponents together. 2 plus 2 plus 6 plus 1 should give you the number of electrons, 11. If it doesn't add up correctly, you made a mistake. So you can always check yourself. Okay, so that's the electron configuration for sodium. Is there any questions or misconceptions about how to do these? Most kids got really good at this. Yeah? You feel confident, comfortable? Good? Okay. All right, the next one is going to ask me for a noble gas configuration. So noble gas of bismuth, because bismuth is way down here. And if we have to start with hydrogen, it would take me forever to get there. So we use the noble gas in front of bismuth. So bismuth is number 83. The noble gas in front of it is xenon. So I'm going to put Xe in brackets. And what that means is start here. So instead of starting all the way up at hydrogen, I'm going to start at xenon and then work my way down to bismuth. Okay, so after xenon, this is the 6th energy level. I'm in the S block, so it'll be 6s2. What comes after 6s2? 4f14. Do you see how it skips in the numbers from 56 to 71? Yes? That's because 57 is down here in 4f. Okay? So it goes from 6s2 to 4f. This is 14 electrons wide. Count them if you don't believe me. But this is very, very forgotten. Okay, kids forget about that all the time. It's a common mistake. Then you'll go up, and the way I always figure out the D block is I just start at the top one and count my way down. I've memorized that this is 3D, so this must be 4D, and this must be 5D. Okay, don't try to just memorize everything. Memorize one thing and count down. All right, so this would be 5D. It is 10 wide. You can count them if you would like. And then, if I know this is 2P, this is 3P, 4P, 5P, 6P. So 6P, 1, 2, 3. Any questions about that? Are you sure? Yes? Okay. Right. So that's all for electron configurations. We can move on to nomenclature, my favorite. Okay, so nomenclature isn't actually that challenging. It's just easy to forget. It's like learning a foreign language, right? If you don't practice it all the time, you're going to forget it. So let's go through some of these. So for ionic compounds, the rule for ionic compounds is no prefixes. If a kid tells me this is tricalcium diphosphate, it breaks my heart in half, okay? Don't use prefixes if it's ionic. It's only molecular compounds that you use prefixes for. Nothing else has a prefix. And by prefixes, I'm talking about like mono, di, tri, tetra, all of those, okay? So this would be called simply calcium. And what's this thing called? Phosphate. So calcium phosphate. Easy, right? Okay. And then also, if you're going in the opposite direction, so I give you something like magnesium bromide, crisscross your oxidation numbers and you'll get your compound. So magnesium, if we look it up on the periodic table, we need to have memorized our oxidation number. Some of you may not even know what the word oxidation number means. It's the charges, okay, of the ion. So +1, +2, +3. This one's variable, and then it goes -3, -2, -1, 0. Okay, so if I find magnesium, it's in the +2 column. And what is it called? Magnesium bromide, right? So bromine is over here and is -1. So that's what I'm going to crisscross. Magnesium, which is +2, with bromine, which is -1. Okay, and for those of you who don't remember crisscrossing, just the number moves, not the charge. So that means I have 1 magnesium and I've got 2 bromines. Questions about crisscrossing? We okay? Yes, ma'am. No, there will never be a negative there. It should just be a whole number. Yeah. And it should be positive number, yeah. So, because what this means is I have 1 magnesium combined with 2 bromines. So it wouldn't make sense if it was negative. Do you see what I'm saying? Yeah. So there are always positive numbers. Okay. All right, for molecular compounds, this is the only one where we do use prefixes. So molecular prefixes. Okay, so this would be dinitrogen. What is the prefix for 5? Penta. Good, like the pentagon has 5 sides, right? So it's dinitrogen pentoxide. It's kind of weird if it's combined with oxygen. It drops the A. So it's just pentoxide instead of pentaoxide. I guess they decided they didn't want 2 vowels together. Okay. On this one, boron trifluoride, there's no prefix for boron, so that just means there's 1 of them. And then tri means 3, so that means there's 3 fluorines. Okay. And don't make silly mistakes like putting FL for fluorine. Please don't do that. Look it up on your periodic table if you don't have it memorized, okay? And the reason I'm saying that is because kids do it all the time. Here's another stupid thing kids do. What is that called? Sodium. What is this called? Sulfur. There's a difference, okay? Sodium, sulfur, okay? Do not call this sodium. Makes me very sad when kids do it, and they do it all the time. I'll have kids that'll do it on the final exam in the spring. You can imagine they come back the next year. Okay. They do. They'll be back. Okay, so with acids. Okay. Acids are a little bit more complicated. They actually have 3 naming rules for acids. And it's all based on what follows the hydrogen. Okay? So acids, we know that they're acids because they start with hydrogen. Okay, so hydrogen, acid, yay. Okay, what's after it is just chlorine. So is this going to have hydro in it or not? Yes. Okay, so the way that I always teach this is here's a periodic table. Okay, on the front of the periodic table, if the part behind the hydrogen is just an element and it's on the front of the periodic table, it's hydro. If it's a polyatomic ion on the back, it's not hydro. Okay, so on the front, hydro, on the back, no hydro. If you can remember that, it's going to help you a lot, okay? So chlorine is just found on the front of the periodic table. So this is hydro. So this is hydroblankic acid, so hydrochloric acid. Okay. So hydrogen, and then after it, if it's on the front, if you want to write down these rules, because this is what y'all are really bad at in general is nomenclature, kids just forget it, write these down. So if it's on the front, then this is going to be hydroblankic acid. That's the rule. Okay, if it's on the back and it ends in 8, does anybody remember the rule? If it ends in 8, what it changes to? Ick. Good. Okay, so it's what I ate was icky, right? It's corny, it's cheesy, but it's going to help us a lot. So if the ending is 8, meaning something like phosphate, it changes to ick, okay? Or if it's ite, do you remember what that changes to? Us. What was the rule on that? The bite was infectious. Good, okay? Or poisonous. We've taught it both ways. But those are the rules for acids. They're very simple. It's just kids forget about them. So here's my question for you now. 18 and 19. These don't have hydro in them. So where am I going to find the part that goes behind the hydrogen? On the back of your periodic table, meaning they have to be a polyatomic ion. Does that make sense? Okay, so if this is sulfuric acid and ick and 8 go together, it's going to change back to 8. So I'm looking for something called sulfate. What is sulfate? SO4, its charge is -2. You're going to crisscross this with hydrogen. So the 2 goes down here, and I get H2SO4. Okay? All right, and then this is chlorus. Us is going to change to ite. So it's chlorite. What is chlorite? ClO2. What is its oxidation number? It is -1. Nice. Okay, since hydrogen is +1, it's just going to be HClO2. Questions about how to get the names of those acids? Are you sure? Okay. The last one, number 20, and then we'll take a break. Okay. In the space below, draw a diagram using dots and arrows to show the transfer of electrons to form the ionic compound between calcium and chlorine. I would say on the last test, this was semi-successful. It wasn't a skill that kids mastered, though, okay? So I want to revisit this for a second when you're drawing these arrows and what it means, okay? First, when you're drawing the dot diagrams, those dots represent the number of valence electrons. So here's the trend for valence electrons. It goes 1, 2, 3, 4, 5, 6, 7, and 8, except hydrogen, which really just has 2, okay? So everything but, I meant helium, has 2. Everything below that is going to have 8, okay? So if I'm drawing the dot diagram for calcium and chlorine, calcium should only have 2 dots for the number of valence electrons. Okay? So I'm going to put a dot here. I'm going to put a dot here. The rule is as long as they're not coupled, it's okay. So you don't want to put the dots together. All right? And then you've got chlorine, which has 7 valence electrons. 1, 2, 3, 4, 5, 6, and 7. All right, so what's going to happen here is they're going to transfer electrons so that they're happy, right? Chlorine wants to have 8 electrons, okay? So what's going to happen is calcium is going to donate 1. Well, chlorine's happy, but calcium's not. Still has one more to donate, so what should I do? Add another chlorine, okay? Add another chlorine so that calcium can give away another electron. Okay. And that's the correct dot diagram. Remember with these, we're grading them by hand, so you want to make sure that your dots look purposeful and make sense. Because if they don't, then it won't be correct. All right. And this is 20% of your final, just this little piece. Any questions about this part of the final exam? You sure? Okay. Let's go ahead and take a 5-minute break.